Okay, and this is our final video in our small little snippet of matrices, which is really just a very brief introduction to matrices, how they work with simultaneous equations, so that we can ultimately get to our next topic of transformations and look at how we use matrices with transformations. Now, geometry of simultaneous linear equations with three variables. To be honest, I think there is some content in this section of your textbook which is not really accessible in methods and which you're highly unlikely to see in a test or an exam or a SAC. Okay. Having said that, we're going to go through it. It's really just an extension on from the previous video. You do not need to be able to understand the geometry of what's happening in three variables. So that's why this is kind of trivial. It becomes very just follow these rules and do this. But I am going to cover it because I have seen systems of three equations in three variables on exams, but it's generally a very trivial question. Okay, so systems of equations with more than two variables can be solved using algebraic methods. Okay, but they quickly become time consuming when we've got three equations and three unknowns, let alone if we have four equations and four unknowns or 10 equations in 10 unknowns. And this is where matrix methods really do become preferable to elimination or substitution and using technology to support that. As I said in the previous video, finding determinants and inverses for matrices larger than 2 by 2 also becomes really complicated and is beyond the scope of this course to do that by hand. So we will utilize our CAS when we have systems of equations with more than two variables, which is why this becomes a bit trivial, because if I want to solve these equations simultaneously and I've got my CAS, I'm just going to use menu 371 and solve three equations for x, y, and z. Okay. Let's have a look though at the different ways that we can do it. So we can actually solve the system algebraically, and it's really just about being systematic and eliminating one of the variables so that you then just have two equations with two unknowns, solving those and then going back to find the third one. So if I call this equation 1, equation 2 and equation 3, the first thing I'm going to do, I'm just trying to eliminate a variable. If I add equations 1 and 2, that will eliminate y. Okay, so I'm going to do equation 1 plus equation 2, and I'm going to get 2x, y plus negative y eliminates y, and then we've got negative 3z plus 2z, and so that is negative 1z, so negative z, negative 10 plus 3 is negative 7. Okay, so that's a new equation. Let's call that equation 4. If I were to also do 2 plus 3, I would create a different equation, but it would also be a different equation without any y's in it. So 2 plus 3 gives me 3x. 2z plus negative z is 2z minus z, so that's plus z. And then equals 3 plus negative 6, that's negative 3. So let's call that equation 5. Now what we've done is we have created two simultaneous equations with two variables in them. And so we can now solve these to find x and z, and then we can sub x and z back into any of these to find what y has to be. Okay, so essentially the algebra is no different, it's just there's some extra steps. You've got to first of all add or subtract combinations of the equations to create two equations with two unknowns, and then you go and solve those. Okay, so again I can eliminate z very easily by adding these. So I'm going to do 4 plus 5, which will give me 5x, z's will eliminate, and negative 7 plus negative 3 is negative 7 minus 3, which is negative 10. And so x is equal to negative 2. And then once we've got x, we can go back into equation 4 or 5 to find z. Okay, so I'm going to sub x into equation 4, which is going to give me 2 times negative 2 minus z equals negative 7. So that's negative 4 minus z equals negative 7. Lots of negatives there. That's 4 plus z equals 7. And so z equals 3. Okay, so we've got x and we've got z. And now that we've got x and z, we're going to sub x and z into any one of the first three equations. Let's just go back to equation 2, the numbers there are a bit smaller. So x is negative 2 minus y plus 2 lots of z, so 2 lots of 3 equals 3, and we can solve this for y. So that's negative 2 minus y plus 6 equals 3, So that is negative y plus 4 equals 3. And so y is minus 1, or sorry, minus 1, or y equals 1. Okay, so therefore, x equals negative 2, y equals 1, and z equals 3 is the solutions of those simultaneous equations. We'll talk a bit about what that means graphically, but you really don't need to know how to, which is why this is all a bit trivial and a bit silly. It doesn't, you're not doing this with any context about what's happening. Okay, we could also set up a matrix equation and use our CAS to help us solve it. Okay, so if we converted this system of equations into a matrix equation, let me just rewrite out the equations. X plus y minus 3z, I think, was that one negative equal to negative 10? Yep. X minus y plus 2z equals 3. And then the final one, 2x plus y minus z. 2x plus y minus z equals, I think it was negative 6. Let me just check that. Yeah. Okay, so if we convert these into a matrix equation, we're going to have, this time it'll be a 3 by 3 matrix with all of the coefficients. Okay. So that 3 by 3, again, making sure that you've got your x's and your y's and your z's properly lined up before you make your matrix. So you're going to have 1x, 1y, and negative 3z, 1x, negative 1y, and 2z, 2x's, 1y, and negative 1z. So when we multiply that by x, y, z, again, you can verify, oh, sorry, did mean to change pen color there. Row times column, 1 times x plus 1 times y minus 3 times z is exactly what's happening here. Okay. All right, and then that is equal to negative 10, 3, and negative 6. So we know that to solve this equation for x, y, and z, so to solve for that matrix, remember if this is A times x equals B, we would be multiplying by the inverse of A to cancel that out, so multiplying by the inverse of A. So x is going to be inverse of A times B. So I'm just going to write that. X is 1, 1, minus 3, 1, minus 1, 2, 2, 1, minus 1. The inverse of that matrix multiplied by minus 10, 3, and minus 6. And so we can then get our CAS to evaluate that for us. So we need a 3 by 3 matrix, so I need this one, and I specify I want 3 by 3, which is the default. And I'm going to have 1, 1, negative 3. I'm just pressing tab to go between those various boxes. 1, negative 1, 2, and 2, 1, negative 1. And we're doing the inverse of that, and then we are multiplying by, now we need a 3 by 1 matrix. So again, we're going to this general matrix here, and changing that to 3 by 1, and then negative 10, 3, and negative 6. And we get negative 2, 1, 3, which means that x is equal to negative 2, y is equal to 1, and z is equal to 3, which was what we got up there. Therefore, x equals negative 2, y equals 1, and z equals 3. However, because you need your CAS to do the 3 by 3 matrix work for you, there's no point in converting it to a matrix equation. However, I have seen multiple choice questions where the question is, here's a system of equations, which of the following options A, B, C, D, E, which of the following matrix equations represents this system of simultaneous equations, and vice versa. Here's a matrix equation, which of the following sets of simultaneous equations are represented by this matrix equation. However, if it's just solve these equations, the quickest way to do that is to just use the simultaneous equation solving. So menu 371, solve a system of equations. I've got 3 equations. The variables are x, y, and z, and I just type my equations in. X plus y minus 3z equals negative 10. X minus y plus 2z equals 3, and 2x plus y minus z equals negative 6, and we get the same thing. Okay, So by solving with CAS, we also get x is -2, y is 1, and z is 3. Okay, so I guess the question is, well, what does this represent? When we solve two simultaneous linear equations, when we get a unique solution, and that's what we've obtained here, we've obtained a unique solution, one set of x, y, z values that work. What does that mean graphically? You know, they're not lines, what are they? So when we have an equation in 3 variables, and I'm only going to touch on this briefly because you really don't need to know anything about graphs in 3 dimensions, but we are essentially working in 3 dimensions. And rather than each of these equations representing a line, they now represent a plane. So a plane is a mathematical surface. It's an infinitely large surface. You imagine a tabletop or a wall in your room going on forever. Okay? Can't change direction. The direction is defined. It goes, if it's a wall, it goes vertically straight up and down, but imagine that it extends forever as one infinite surface. Okay? So that's what each of those is representing. So therefore, when we're trying to solve 3 of those, we're looking at how do 3 surfaces interact in 3-dimensional space. So imagine looking in your room, for example, at a corner of your room. So that's where you have 3 surfaces intersecting at one point. If you look up at the ceiling and look at one of the corners in the room, you're going to have 2 walls and the ceiling, 3 surfaces that are intersecting at that one point in the corner of the room. Okay? The other things that could happen, and so that's a situation where your 3 planes all intersect at one point, which is what we found in the previous example. They all intersect just at one point. What could also happen is they might intersect along a line. So that might be, again, sort of looking around the room that you're sitting in. If you imagine 2 walls where they intersect along a line, if you imagine sort of holding a third infinite piece of paper also intersecting along that same line. So all 3 planes are intersecting along that same line. Okay. So they might intersect along a line, which would mean we would get infinitely many solutions. Infinitely many solutions. This, where they just intersect at one point, this would be a unique solution, which is what we found in the previous example. However, the 3 planes might not intersect at all. There might be no points in the 3-dimensional world where they all intersect at the same time. The most obvious way to think about that would just be 3 parallel planes. But there can be also other situations where 2 of the planes intersect, but they never all intersect at the same place. So for example, here we've got 2 parallel planes and a third plane cutting through them. Now, the first and third planes intersect at a line, the second and third planes intersect at a line, but there's nowhere where all 3 intersect. So the system of equations in 3 variables wouldn't have any solution. So all 3 of these would be no solutions. Okay? Again, you've got a situation here where, this and this plane intersect, this plane and this plane intersect along a line. It's hard to tell how this is actually drawn, but the other 2 don't intersect at all, or they also intersect at a line, but no, again, the 3 planes don't ever meet at the one point. Okay, you don't need to know the geometry of what's happening, but you do need to see that it is still possible when you have 3 equations in 3 unknowns for there to be a unique solution. That is where you can find a combination of an x value, a y value, and a z value that works, or infinitely many solutions, or no solutions. Okay, and again, the infinitely many solutions and the no solutions are going to come from situations where our determinant equals 0 if we've set the equations up as a matrix equation. Okay. So let's just go back to 2 by 2 for a minute so we can see what happens when we get infinitely many solutions. Because when we have a system of equations that has infinitely many solutions, it is customary to express these solutions in terms of a parameter. And that's what your CAS does. You see that. In fact, we did one in the last video where I got the CAS to solve the simultaneous equations that represented the same line, and our CAS did something that looked a bit interesting or strange or scary, potentially. It's not. It's doing good maths. So let's have a look at what we mean by representing the solutions in terms of a parameter. Okay, so if we have a close look at these equations, they're the same line. The whole equation multiplied by 2 and we get the second equation. Okay, again, they're not in the same order. It's the same pair of equations we looked at in the previous video. 2x plus 3y equals 6 and 4x plus 6y equals 12 if we line them up. So the whole thing is just being doubled. Okay, so we know there's going to be infinitely many solutions. So one way we can express that is to introduce a parameter, and conventionally if we've got two variables we usually let y equal the parameter. And often we use this Greek letter called lambda as a parameter. You could use another letter. Your CAS uses n and c sometimes for parameters, and we'll see that in a minute. So I'm going to introduce a parameter by letting y equal lambda. Alright, now it doesn't matter which equation I go to, I'm going to go into the first equation and I'm going to let y equal lambda, which means that 2 times x plus 3 times lambda is equal to 6. Okay, and if I now express x in terms of lambda, 2x equals 6 minus 3 lambda, and x therefore equals 6 minus 3 lambda all over 2. Or you could write that as 3 minus 3 on 2 lambda, however you want to write it. So now we've come up with a general way to describe all of the infinitely many solutions. Okay, x is equal to 6 minus 3 lambda over 2, and y is equal to lambda. So for example, when when lambda equals 0, we're going to get x equals what will that be? 6 on 2, so 3, and y equals 0. So that is one of the infinitely many solutions to that equation. When lambda equals 1, we get the solution 6 minus 3, which is 3 on 2, so x equals 3 on 2, and y equals 1. When lambda equals 10, we get the solution 6 minus 30, so that's negative 24 on 2, which is negative 12, and y equals 10, because y is lambda. Oh, sorry, my apologies. That, and okay, again. So you could look at when x equals 7.8, when x equals pi, sorry, not lambda, when lambda equals 7.8, when lambda equals pi, when lambda equals root 2, when lambda equals 7.398, when lambda equals negative 65. All of those are going to give a pair of x and y values that are one of the infinitely many solutions. So this is a general way to describe those infinitely many solutions. Okay, and when you use your CAS does this. So if we got our CAS to solve this pair of equations, menu 371, two equations with two unknowns, 2x plus 3y equals 6, and 6y plus 4x equals 12, it gives us this. It's using C2, where I used lambda. I wouldn't write C2 on the paper. If you're going to copy out that answer from your CAS, you're going to write that x equals negative 3 times lambda minus 2, or generally speaking I would say use Greek letter lambda or letter n. They're common ones we use as parameters. You can use t, sort of has different implications, but yeah, just don't write C2. Okay, you could write C, but generally I'd go with lambda or n. So therefore, that is what I would write on the paper, and let's be clear about the fact that that is the same as that if you expand out the bracket on the numerator. Okay. Alright, so I guess the key really about that, I think, is more about you not freaking out when your CAS gives you things that look like this, and understanding that actually what that's telling you is that there are infinitely many solutions, and those infinitely many solutions all follow this same pattern. The x value will be negative 3 times the y value, take away 2, all over 2, and the y value will be the y value. So as I said, that's that. So final example here is just the simultaneous equations below have infinitely many solutions. Use your CAS to describe these solutions through the use of a parameter. So you would simply just solve the three equations for x, y, and z using your CAS, and it will give you the solution in terms of a parameter if there's infinitely many solutions, which the question tells us there is. Okay, let's just type these in, nearly there. X minus 3y plus 2z equals 2, and negative x minus 4y plus 7z equals 17. Enter. Okay, so it tells us that x is equal to negative, now I'm going to write it out as the CAS writes it, but then I'm going to write it the way a human would write it. Negative 13, we'll replace the C3 with lambda. Now it used C3 in this next equation, and that's just because it used C2 in its previous solution. It's distinguishing that the parameter I'm using here is different to the one in the previous question, but the 3 doesn't mean anything. It's not 3 times C or anything. It's just the third C variable. So we've got 13 times our parameter, I'm going to call it lambda, minus 43. Our y value is 5 times lambda minus 3, and our z value is lambda. So again, this is horrible. Your CAS loves to factor out negatives unnecessarily. I would write that as negative 13 lambda plus 43. So I'd write that as 43 minus 13 lambda. Similarly, this one I would expand that out to 5 lambda minus 15, and this one is just lambda. Okay. So these would be my not three solutions, sorry, it's the one solution, but there's 3 parts to the solution because there's 3 variables. Okay, some questions from exercise 2G.